Hello, my name is Tim Jacobs, and I'm the Director of Research Science for Amazon Transportation Services. We at Amazon are honored and excited to be the recipient of the 2021 Informs Prize. To give you an idea of how we actually use operations research and analytics at Amazon, a couple of my colleagues, Nile Bulbul and Mauricio Resende, and I are going to give you a short overview of some of the techniques and some of the areas where we use operations research and analytics. And then we're going to dive into some specific areas dealing with the middle mile space, which involves the movement of inventory from fulfillment centers to sortation centers and delivery stations. But to start, let me give you a short video to show you some of the activity that goes on in moving our inventory from a fulfillment center and onto an airplane for delivery. I hope you found that exciting. To give you an idea of what we're going to talk about today, first we're going to start with what is Amazon, give you a brief history of how we use operations research and analytics at Amazon, give you an idea of the breadth of areas that we actually apply some of these techniques within the company. And then we'll dive in and dig in a little bit more into the middle mile space of moving inventory and packages from a fulfillment center to a sortation center or a delivery station and so forth. And we'll talk a lot about the research and development that is done in those areas. And we'll give you a few examples of that, considering surface research science, air science and tech, and marketplace science. So to get us started, I'm going to turn it over to Mauricio, who's going to give us a brief overview of the history of OR and analytics at Amazon and some of the breadth. Mauricio?
So thank you, Tim, for the introduction. So Amazon strives to be the Earth's most customer-centric company by offering a wide selection of goods and services, search and discovery, low prices, and speedy delivery. At Amazon, we start with the customer and work backwards. The company was founded in 1994 in Bellevue, Washington, and currently has two headquarters, one in the west coast of the United States in Seattle, Washington, and another one in the east coast in Arlington, Virginia. Most of you know Amazon as a global retailer. However, Amazon is also a technology company and a marketplace. Amazon is a cloud computing and storage company. It's a publishing company, a hardware company, an entertainment company, a healthcare company, and a physical store company, just to name a few. In this talk, though, we're going to focus on transportation for the retail business. So we'll give examples of how OR and analytics can support the expansion of the worldwide transportation network. And always having in mind that we want to deliver to customers faster, cheaper, and on time. So OR was introduced at Amazon in the late 1990s and early 2000s. At that time, Amazon was mainly a book and CD seller. Transportation was mainly done by third-party carriers. OR was applied in determining the location of fulfillment centers so-called FCs, which are Amazon's warehouses, and improving the throughput of these FCs. As storage became a problem, OR was used to make better use of the existing infrastructure. Two early major contributions of OR at Amazon were F2P, or Fulfill to Promise, which takes an order and determines which FC is assigned to the order, such that the delivery date promise of the customer is met. And Adaptive Transportation Optimization Service, or ATROPS, optimizes the ship methods during the fulfillment process. These systems operate in real time and are triggered millions of times a day. So OR is applied throughout Amazon. Without OR, the growth Amazon has experienced over the years would not have been possible. For example, Amazon Web Services, or AWS, uses OR to design communication networks, to analyze packet flows on its backbone network, and to manage inventory of parts for its data centers. Physical stores applies OR to locate new stores, to forecast demand, and to manage inventory. Other examples of OR at Amazon include labor scheduling, maritime transportation of goods from overseas suppliers to fulfillment centers, railway transportation of goods, and robotics at Amazon Robotics. In the early days, Amazon relied solely on third-party carriers for its transportation needs. As the company's operations grew, it became clear that Amazon had to build its own transportation and delivery capability. OR has been involved since the start. The Amazon retail network consists of fulfillment centers that are spread out geographically, where goods are stored and where fulfillment starts. In addition, there are sortation centers where packages originating from different fulfillment centers and having a common destination are sorted and loaded into a trailer to a delivery station near the customer. Fulfillment centers, sortation centers, and delivery stations are Amazon facilities connected by one or more modes of transportation, the most common of which are tractor trailers. Packages are loaded onto trailers at fulfillment centers and are transported either to a sortation center or directly to a delivery station. Tim will now continue by describing some of our air cargo airline, as well as the team that he manages, MMPROS.
Thanks, Mauricio. As Mauricio has mentioned, oftentimes we find that packages have to travel larger distances than it's actually feasible to use ground transportation. And in those cases, we flow packages over the air network. And our air network consists of a number of gateways and hubs. We use a hybrid network design of point-to-point and hub and spoke to actually connect all the all the fulfillment centers and delivery stations that we need to consider. And so that actually gives us the most efficient approach to actually running the overall cargo air service. By definition, middle mile transportation is the movement of goods between Amazon facilities. So from a fulfillment center to a sortation center, from a fulfillment center to a delivery station, or from a sortation center to a delivery station. We don't include in middle mile the delivery of packages to your house. That is called last mile. And in this case, so what we're going to focus on here is some of the operations research applications within this middle mile space and some of the research and development work that we're doing in that area. So as we said, we're going to look at the impact of operations research and applied mathematical modeling, things like stochastic modeling. How do I do network design? How do I do network operations? How do I look at network recovery in the context of disruptions due to weather events or maintenance events and so forth? Okay. Our middle mile network represents one of the fastest growing logistics problems that Amazon deals with every day. We deliver more than 100 million packages per week using more than 20,000 daily truckloads and more than 200 daily flights within North America alone. The operational scale challenges us to actually design and operate the most robust transportation network that minimizes our overall costs while meeting all of our customer promises. So to do this, we have a group of scientists called MMPROS, the MMPROS team, and they are charged with the optimization of the design of our current and our future air and ground networks, the optimization of package flow throughout the network or within the network, designing effective disruption management policies and to handle things when we do have a weather event, like a snowstorm that shuts down part of the network, or if we have other smaller disruptions which could be due to a maintenance event, and so forth. They're also charged with effectively aligning the capacity and the demand to the demand of the network through dynamic pricing and resource allocation. So we have a lot of things that happen when we do the planning, but there are a lot of disruptions and things that occur that require us to do things more dynamically in the day of operations. And lastly, we are also charged with looking at the strategic research towards new business opportunities, new network designs, new ways of actually operating the middle mile space. That also includes looking at the integration between an air network and a ground network, or air network and a rail network. It doesn't help us to operate these type of networks in silos. To have an effective and efficient solution, we have to integrate them. So the MMPROS team stands for Middle Mile Planning, Research, and Optimization Science. And 4 or 5 years ago, when we started this team, it started with, there were 4 of us or so on the team. And today we are right around 100, a little under 100. We have a director of research science, we have 3 research science managers, we have 22 research scientists, including 7 internationally recognized research experts and leaders. We have 8 applied scientists, 7 data scientists, numerous software developers, development engineers, and program managers. The organization's members participate, and a number of them are fellows in organizations like ACM, AGA4s, Informs, and SIAM. In addition, we have involvement with the Frontiers of Engineering program at the National Academy of Engineering, and a number of our members participate as on the editorial boards of journals such as Operations Research and Discrete Optimization. Interestingly, 1 out of 4 of our scientists are women, and our scientists come from over a dozen countries around the world. The MMPROS team is built on 3 major areas. One is surface research science, and that covers middle mile ground transportation and how we model that. How do we route trucks? How do we determine how to balance the network over time? How do we determine where and when we should operate empty loads, or what we call backhauls? Then we have the air science and tech team, and the air science and tech team covers how do we design the air network? How do we determine where the hub has to be? How do we determine what kind of sortation needs to take place either at a gateway or at a hub? And then how many aircraft do we need? Of what type of aircraft do we need? And so forth. How do we do maintenance routing? How do we plan fuel? How do we do fuel planning across the board. And the last area that we have is what we call marketplace science research. And marketplace science is actually the area where we're dynamically doing pricing of our loads and trying to figure out how do we dynamically price our loads in such a way that we align our needs in terms of shipping loads with carrier availability and carrier supply. And with that, what I'm going to do is now I'm going to turn it back over to Mauricio to give us an idea and start walking us through some of the surface research science that we do.
Thanks again, Tim. I'll describe now one of the problems that we have to solve at MMPROS. And this is the middle mile routing scheduling problem. In this problem, we're given a set of facility and driver domicile locations, pairwise distances and transit times, and other parameters related to the facilities like open hours. Supply of drivers, each with a domicile location, a driver type, and a cost model. We're given also a set of demands of full truckloads. Each demand has an origin and destination, a pickup and drop-off time window, and a trailer type. And as a result, we want to produce efficient schedules that satisfy government rules, operational constraints, lifestyle constraints. Now, this problem is different from the capacitated or first or last mile problem. Let me show you some examples of lifestyle and operational constraints. As an example of a lifestyle constraint, a driver may want to return home every K days. Some drivers like to return home every day, others every other day, and so on. Biorhythm constraints state that work will have to be started at around the same time of the day, every day over day. Operational constraints are things like facility open hours and the fact that every closed loop has the same equipment type. What are some examples of cost models? Well, one can pay by mile, can pay by shift, can have overage. For example, $100 for the first 50 miles and then $1 per mile over 50 miles. Fuel surcharge, prepaid shifts. And what are the requirements of our solution methods? Well, we have to be able to handle very large instances with up to 100,000 truckloads. We need to enforce all the constraints. Some of these constraints are required by law. We have to support multiple regions, North America, Europe, for example. We have to handle be able to handle heterogeneous driver pool. And our solution has to be produced rather fast. And what solution methods do we use for solving this problem? We make use of techniques based on stochastic local search, such as iterated local search, distributed computing, where we distribute the computation to different compute nodes and then put the solutions together again, and column generation heuristic. So this was an example of a problem that we have to solve in the surface research. Nilaya now will talk about a problem that she faces in air, science, and tech.
Everyone, in this part of the talk, I will briefly discuss a particular resource allocation problem for Amazon Air recovery operations. As mentioned earlier, we have optimization tools to construct network execution plans, which play a critical role in achieving high customer service targets. However, deviations from such plans are unavoidable in execution due to the uncertain disruption events. And it is well known that there is a wide variety of events that can cause disruptions and delays in the scheduled flight arrival and departure times. And such delays have a direct impact on the on-time delivery performance. Aligned with the customer obsession principle, improving the on-time performance is one of Amazon Air's central goals. Reserving additional resources such as spare aircraft and spare crew is an effective practice. We can consider the spare aircraft and crew as very expensive resources sitting idle until there is an emergency call. And utilizing such resources just for recovery operations proves to be useful to minimize the deviations from the planned schedules and mitigate the cascading effects of the disruptions on the downstream operations. In this context, Amazon Air relies on spare aircraft strategies to support the disruption recovery management. And the particular problem of interest is to find the optimal locations of spare aircraft along with the crew schedules. It is a significant resource allocation problem considering the fact that only a limited number of aircraft can be spared due to their high cost. Here we see an illustrative spare plan. It provides decisions on the locations and types of spare aircraft along with their subfleet assignments. We have two types of spare, hot and cold. A cold spare doesn't require a reserved crew. In this case, spare can only be used to recover a flight sharing the same carrier so that originally scheduled crew can fly the spare aircraft. On the other hand, a hot spare is associated with a reserved crew. For example, a spare crew can fly the spare aircraft to recover a flight departing from another gateway. Accordingly, the spare plan also provides the crew window of schedules, indicating the time periods during which we can call for a crew in case of a disruption. We have a coverage-based location and scheduling model. Towards finding the best decisions, we consider multiple performance measures, including different types of flight coverage metrics. Let me first note that the flight schedule itself can provide swapping opportunities known as virtual spares if two aircraft share a sufficient amount of ground times. And spare planning aims to complement such existing backup options and focuses on origin and ferry coverage by additional physical spares. In a nutshell, our objective is to cover the maximum number of flights and packages while minimizing the overall cost and satisfying a set of operational constraints. For example, we honor the crew duty limitations and certain departure curfews. Let me also note that we consider certain time restrictions and time input to identify different types of coverage options at the network level. Considering the combinatorial structure of the problem and the growth trend in the Amazon Air, we needed to develop an effective modeling approach, and there is no available third-party solution. We formulated our problem as a bilinear program. It provides a flexible decision support to balance the conflicting multiple performance measures. For example, it captures the relative significance of different types of coverage. It also allows us to distinguish the priorities of the flights. And to this end, our approach integrates the package flow plan into spare planning, which is a novel development. Finally, let me share a few highlights on the business impact. Our optimization tool was fully adopted in May 2020, replacing the previous approach of manually evaluating a limited number of candidate solutions. and it provides better solutions in terms of the network coverage without increasing the number of spare aircraft despite the increase in the flight number. For example, the previous peak holidays, for the previous peak holiday season alone, it reduced spare costs by more than 7%. Thank you. And Tim will continue with marketplace research.
Thanks, Nile. And so for our last section, our last thing that we want to talk a little bit about is what we call middle mile marketplace science. And this deals with how do we actually look at the marketplace and actually how do we align, how do we do the most efficient alignment between the supply that's available, whether it's a carrier or whether it's an aircraft or an air service, and the actual demand, the package demand that we have. And that can be demand that is our internal demand. It can also be vendor demand coming into us and so forth. But that's what we call marketplace science. Now, if you go back 3 or 4 years ago, I think probably about 4 years ago, it was really, in the beginning, it was kind of a mess. What would actually happen is that if you look at the trucking network alone, and you had spot loads, things that came up at the last minute. Oh, we need an extra truck to go to drive between Phoenix and Ontario, California. That oftentimes what we would do is we would toss these loads out onto a number of different load boards. And then these load boards were bidding sites. So carriers would bid on them. And then we had a manual brokerage team that actually had conversations and negotiated the final price and the timing of the loads. And so the process was like carriers would identify potential loads that they wanted to carry. They would place bids, the lowest bid would win, and our brokers would then have a conversation with them to finalize the price. Very manual, very tedious, not very efficient. So what we did, we wanted to get into that, we had started identifying a number of problems in this area. And that was that you had a limited number of carriers that had access to the loads, right? Because it just wasn't scalable. You had no historical record of prices that you could actually use. You could imagine that if a broker A was negotiated a price with the carrier on one day, and broker B negotiated a price on the second day for the same origin to destination load, but on a different day, you could imagine one time the price might be, one thing, and the next day it might be 50% more or 20% less. There was just no rhyme or reason to it. We would have to rely on a number of load boards, and we'd have to rely on bidding. And then we'd have to shore that up with brokers doing manual work to negotiate and settle everything. And that led to a lot of problems. Carriers could game the system and so forth. As a result, we ended up with higher costs, less flexibility, and a lot more risk. So what we decided to do is to tackle this, is to change the way that system works. And so we went to what we know as the relay load board today. The relay load board does not allow bidding. So what happens is we dynamically, we use a combination of machine learning and optimization to actually figure out what is the best possible price to put out on the market. And we surface that price, and then carriers can look at it, and they don't have to accept it. They can say, well, I'm going to wait and see if the price goes up, and then I'll take it. But that they have to realize, and they do realize, that at the same time, there might be 100 other carriers now looking at that same load, and that might be an okay price for them. So that actually helps us actually get a lower, more efficient price. It also expands the access to a lot more carriers. Today, we have well over 10,000 carriers that use our system for this. Our combined use of ML and traditional optimization incorporates uncertainty. It allows us to the stimulation of supply through the dynamic pricing. It uses feedback. We have an active feedback loop that continues to get us, that helps us make sure that our price is a fair price out on the market. As a result, we have access to thousands of carriers, have access to our loads in the spot market. The carrier experience has been much better. So we have a well over a 98, 99% acceptance rate of those loads and those prices. We have better coverage and we have lower costs. Looking forward, we want to expand this. We're in the process of expanding these ideas now across looking at better ways of aligning supply and demand in a dynamic world, not just for spot loads, but spot loads and contract loads, longer term plan loads, and so forth across different modes of transportation, whether it's trucking or whether it's air or whether it's a combination of the two. And that is through, allows us to do dynamic pricing. It allows us to do multiple supply types. So we can actually think about things in terms of a 53-foot semi truck versus a box truck versus an aircraft. We can handle internal and external demand. It gives us the opportunity to do supply demand mix optimization. So instead of, how much should we really have on the spot market? How much should we do contract loads for? And how do we actually balance that over time so that we minimize our risk and the risk to the carriers for cancellations? And then that also allows us, we're doing some very innovative things in how we incorporate machine learning and optimization together, rather than the traditional way of, hey, I've got a machine learning algorithm that gives me inputs to my optimization, or I have my optimization model that gives me an output that goes into a machine learning algorithm. We're looking at more in terms of how do you use machine learning to define the state space or the feasible region within the optimization process. As a result, we end up with lower costs. We end up with better prices for shippers, better work experience for the carriers, less risk, and a lot more flexibility. So with that, we'll conclude. I want to give everybody thank you for your time, and we're happy to entertain some questions for you. Thank you very much. We'll talk soon.